The difference from best to worst ranges from 12x to a whopping 200x for the small and large matrix respectively. Lambda functions are great. Whenever you need something small done, you just write a bit of code and deploy it into the cloud. No need to care about servers, complicated setups, or scaling. Lambda will do the work for you, as long as you can break it down into shorter than 15-minute chunks. This has led many companies to abandon servers altogether and go serverless. But there's the flip side to this coin. Amazon itself has stepped into that problem with their Prime Video service. To show you how to get around this, I collected the most common helper tasks from popular areas: machine learning, statistics, data science, and more. And I will show you exactly what language and package to choose to get the best bang for your buck. Lambda pricing is straightforward. You get billed in gigabyte seconds. That means however much memory your function used and for how long. The smallest memory is 128 megabytes. So if your function ran for 1 second, you'd be billed this number. And if you divided your workload into neat 15-minute chunks and ran them one after another, covering an entire month, you would pay this much. Now, when we look at what an EC2 instance would cost us, we have to think about what resources Lambda actually provides us with. According to the 2021 reInvent, the number of vCPU allocated to a Lambda function is based on the memory allocated. Up to 1.8 gigabytes, we get a single vCPU, and it goes all the way up to 6 vCPU from roughly 8.8 to 10 gigabytes. This leaves us with these 4 EC2 machine sizes to compare it to. And we see that Lambda sets us back about 2 to 8 times of what a permanent on-demand server would cost. Now, this is a very rough comparison, as we don't have to account for the operating system usage on Lambdas, while at the same time we will have to pay for cold start times. According to this study, AWS will put your Lambdas to sleep after about an hour of non-usage. The amount of memory we allocate can sometimes also have a direct impact on the cost effectiveness on a function. For example, this study tested a particularly memory-heavy implementation of calculating Fibonacci numbers. Granted, it's not a very realistic task, but it goes to show that the quickest execution won't necessarily result in the best cost-performance trade-off. Now, let's talk about the test setup. I prepared a repo that you can try out yourself. It will automatically create ECR repos and Lambda function, run them, and extract the build usage. So, in my tests, every use case, every language and library used to create their own Docker image using the newest Amazon-provided base images, and as little additional installs as possible. For our first case, I tested a simple image conversion. This could be a Lambda that runs many times in any given application. It will take a JPEG from S3, resize it, crank up the saturation, and blur a section. So we observe kitty privacy. The results came as a surprise to me, with Python's Pillow library delivering the best results in terms of cost efficiency. Extrapolated to a billion calls, we get prices ranging from $863 to almost $3,000. A 3.5 times difference for a very simple operation. Next, we have a simple data conversion task, converting a CSV to JSON. I tested a CSV with 10,000 cells as well as the larger one with 6.2 million cells. For the smaller one, the difference is very small, but gets substantially larger for bigger CSVs. Coming in at $440 and $1,200 each, Node takes the win with the Pandas library. We award Go a point as well for being very close. Next, we have 3 common machine learning and statistics tasks. For FFT, Go takes the lead, from being 12 to 30 times cheaper than a Node implementation. For the matrix inversion, I tested the highest number of different languages and libraries, as the results kept surprising me. The clear winner ended up being Go with the GoNum library. The memory usage is very small and the timings are phenomenal. The difference from best to worst ranges from 12x to a whopping 200x for the small and large matrix respectively. Now, it seems clear that the algorithms not all have the same computational complexity, and this accounts for the growing difference with larger matrices. Nevertheless, when using a library for a quick implementation of such a standard task, the end result is what's important. When calculating the k nearest neighbors, we see a similar picture, with Go ahead, but this time clearly followed by plain Java for a large series. A Node implementation with MLKNN is only about 60% more expensive than Go. And finally, we have 3 more benchmarking tasks. First, sorting a list of floating point numbers with a similar winner. Then, calculating Fibonacci numbers, where we surprisingly see Python in the lead, followed by Go and Node.js. By creating a SHA hash from a string, in the beginning we see go in the lead for smaller input strings. For larger strings, Node takes the lead with the Crypto.js library, closely followed by Java with JavaSec and Python's hashL library. And finally, a simple read of a text file from S3, where again Go takes first place. Well, what do all of these results tell us? If you are architecting a serverless project or just automating small tasks with Lambdas, it can make a huge difference what technology you choose. Factors that influence the result and cost range from code start times, the computational complexity of the algorithm used, the memory usage of certain packages, or the language runtime as a whole, and in general, if the language is interpreted or compiled. Languages like .NET or Java did surprisingly badly in comparison to Go. While they should have similar advantages, they're not able to compete. Also, surprisingly with some tasks, both Node and Python deliver the most cost-effective results. If you're interested in AWS and AI, check out my other videos on this topic, like this one explaining how to make your own chatbot in a few minutes. Alright, bye.